In the previous parts, we have formulated the learnings of SVM as an optimization problem. Now let's move on to see how we can actually solve this optimization problem and learn the parameters W and B. Remember that in SVM, we have an optimization problem where we want to find the optimal W and B such that we can minimize this objective function subject to these linear constraints. And a standard way to do this is to use a solver. And a solver is just a piece of software for finding solutions to common optimization problems. For example, here we are having a quadratic optimization problem. Therefore, we would need to use a quadratic solver to minimize a quadratic function subject to some linear constraints. But the problem is that solvers are usually inefficient for big data because they are not customized for a specific problem. So how do we implement our own algorithm to minimize this objective function, J of W and B? And just to recap, this objective function has two parts. The first part is basically the margin, and the second part is the empirical loss or the penalty for fitting the data incorrectly. So the idea, of course, is, as usual, we can use the gradient descent. And in gradient descent, we'll need to compute the gradient of this objective function with regard to the jth entry of W. So basically, we can compute the gradient as the sum of two terms. The first term, of course, is W because this is W squared. Therefore, the gradient, of course, will be W. And the second term here would be the gradient of this empirical loss, L, of xi, yi here, with regard to Wj, which is the jth entry of W. And remember that we're actually using the hinge loss here. So basically, if this margin y times W times x plus b, the margin, if it's larger than or equal to 1, then the gradient, this gradient term will be equal to 0. And this corresponds to this flat line here. And otherwise, if it's like smaller than 1, then the gradient of this empirical loss with regard to Wj will be minus yi times the jth entry of x. So this corresponds to the linear part here. And to summarize, using gradient descent, we can have the following algorithms, right? We can iterate the following steps until convergence. And these are just a for loop where we loop over all the entries of the vector W. So in the W, we have d dimensions. Basically, for each dimension, we'll just evaluate the gradient of the objective function with regard to that specific entry. So as we mentioned before, we have compute the gradient as the sum of two terms. The first term will be Wj, and the second term will be the gradient with regard to Wj. And we'll just update the W using the gradient. So the new W will be the OW minus eta times the gradient. So remember that this eta here is the learning rate parameter, or sometimes we can call it the step size. The problem of this algorithm, this gradient descent algorithm, is that to compute the gradient, even with respect to only one entry of W, it takes O(n) time, where n is the size of the training data set. So this is extremely slow. You will need to go over the whole data set before you can update the W for once. So, and to address this problem, we can use stochastic gradient descent. So in stochastic gradient descent, instead of evaluating the gradient over all the examples, we will evaluate it for each individual training example. And this way, you don't need to wait until you finish going over all the data points before you can update the W for even once. You can just update the data, update W even after looking at only one data point. So remember that in the previous gradient descent, we have this summation here with sum over all the data points. And in this stochastic gradient descent, we don't have this summation over I here anymore. So the computation of the gradient is much, much more efficient. So in terms of implementation, this algorithm will become a double for loop. So we'll just iterate these following steps until convergence. And in each iteration, we will go through all the data points and we'll go through all the dimension of W, and we'll just compute the gradient of the objective function with regard to this specific data point and with regard to this specific entry of W. So computing this is extremely fast. And then we can, after just computing this small point, we'll just go ahead and update the jth entry of W. We can, and again, we update it as the Wj minus eta times the gradient. And eta is, again, the learning rate parameter. And in practice, this stochastic gradient descent actually works very well, and also it's much, much faster than the gradient descent.